Hello, everyone. I'm Li Dong from the Natural Language Processing Group at Microsoft Research Asian. Today, our talk is about large-scale self-supervised pre-training from language to vision. First, let's look at the definition of large-scale self-supervised pre-training. First, large-scale means that our data and our model, the size is quite large, which supports various tasks. And the second term is self-supervised, which means that the training signal is from unlabeled data, such as the Wikipedia text corpus or a bunch of code crawled from the GitHub. And the third term is pre-training. It's a new paradigm compared with traditional machine learning methods. The paradigm is that we first pre-train a large-scale model on a very big corpus, and then we can fine-tune the obtained model on our desired end tasks. So for summarization, there are three key elements for the self-supervised pre-training. The first one is data. The data can be text corpus, can also be images, can be speech, can also be code. And the second element is the model architecture. The model architecture we can use, for example, ResNet. We can use the transformer architecture. And for the pre-training task, we often use the denoising auto-encoding style training tasks. And we can also use some contrastive learning style tasks. With all these three key elements, we got a very strong pre-training model. First, let me introduce our first work, which is called Unified Language Model Pre-training for Natural Language Understanding and Natural Language Generation. As shown in the slide, we use a unified modeling based on the transformer network. Then, based on the unified modeling, we can use different self-attention masks to control the access to context for each word token in different variants of language models during pre-training and for different natural language understanding and generation tasks. After pre-training, we can fine-tune the unified model as a bidirectional encoder or as a unidirectional decoder, or even as an encoder-decoder for sequence-to-sequence learning. And for the second work, I would like to introduce the Unified Language Model V2, which also implements the Unified Language Model pre-training. But the difference there here is that we propose a pseudo-masked language model to efficiently implement the Unified Language Model pre-training for various objectives, such as the auto-encoding one or the autoregressive one, or partially autoregressive one. With such powerful modeling technique, we can jointly train these two kinds of objectives together, so that we can fine-tune them on various downstream tasks. And the third work, we try to extend the unified language modeling to the multilingual setting, which is called the InfoXLM, which is a cross-lingual language model pre-training methods. The model is pre-trained on about 100 languages, and we use a multilingual corpus as our pre-training data. And then we use masked language modeling and translation language modeling as the pre-training tasks. In addition, we propose a cross-lingual contrastive learning task to retrieve the similar cross-lingual pairs from the large corpus. After such kind of pretraining, we can fine-tune the model on just the English, and then try to test the fine-tuned model on other languages. Such cross-lingual zero-shot transfer is quite useful, especially when our data set and the task is quite small. So based on the previous work from our group, we can summarize the key observations from such kind of language pretraining. First, the key observation is that transformer becomes a dominated backbone network. The observation is quite important because we found that when we would like to use a very large-scale network, transformer is the current best way to enlarge your network to memorize the data set so that we can get a very powerful model. And the second observation is that generative tasks play the most important role. Although we also use contrastive learning in our InfoXM work, but we can still notice that the most important pretraining task is still the denoising autoencoding style pretraining objectives, such as the masked language modeling or translation language modeling. And the third key observation is that multilingual pretraining can be well handled by the pretrained models, which also a very good property for such kind of pretraining. So a natural research question is that whether we can translate the success from language to vision. For the first observation, the vision transformers are emerging in the vision community. There are many related work such as BEiT, DEiT, or swing transformers for working on this topic. And for the second one, for the generative pretraining task, in the vision community, we are still relying on the contrastive learning or some other similarity-based pretraining methods. So the mainstream algorithm is still not the generative tasks. And for the third observation, we can find that if we treat the images as a foreign language, maybe we can also train. We can unify all the pretraining tasks for both language and images. So in this talk, we would like to talk about our latest work, which is called BEiT, BERT pretraining of image transformers. So as shown in this slide, for these three key elements of the pretraining, we turn to the denoising autoencoding idea to pretrain vision transformer, which has not been well studied by the vision community. It's challenging to directly apply BERT-style pretraining for image data. First of all, there is no pre-exist vocabulary for vision transformers input unit, which is often image patches. So we cannot simply employ a softmax classifier to predict over all possible candidates for masked patches, because the whole search space is so huge. In contrast, for the language vocabulary, such as words or BPE, it's well defined and is autoencoding style pretraining. A straightforward alternative way is regarding the task as a regression problem, which predicts the row pixels of masked patches. However, such pixel-level recovery task tends to waste modeling capability on pretraining short-range dependencies and high-frequency details. Our goal is to overcome the above issues for pretraining of vision transformers. We use we use vision transformer as our backbone architecture. We split an image into fixed size patches and then linearly embed each of them at position embeddings and feed the resulting sequence of vectors to a standard transformer encoder. The encoder contains multiple layers of transformer blocks. The output vectors of the last layer are used as the encoded representations for the image patches. Then we can add a softmax classifier to perform classification by conditioning on the output vectors. Similar to natural language, we represent the image as a sequence of discrete tokens obtained by an image tokenizer. Instead of raw pixels, we learn the image tokenizer via a discrete variational autoencoder. There are two modules during vision token learning. They are tokenizer and the decoder. The tokenizer maps image pixels into discrete tokens according to a visual codebook, and the decoder learns to reconstruct the input image based on the visual tokens. Because the latent vision tokens are discrete, the model training is non-differentiable. Gumball softmax relaxation is employed to train the model parameters. Then we will describe the whole BEiT pretraining process. The proposed self-supervised learning task is named as masked image modeling for each input image. It has two views of representations in our method, namely image patch and the visual tokens. The two tabs are used as input and output representations during pretraining respectively. Notice the number of visual tokens and the number of image patches for one image are the same, where the correspondence relations are utilized during pretraining. Next, we randomly mask approximately 40% of all the image patches, rather than randomly choosing patches for the masked positions. We employ blockwise masking in our work, which is for each block. We set the minimal number of patches to 16. Then we randomly choose an aspect ratio for the masking block. We repeat the above two steps until obtaining enough masked patches. The blockwise masking was also widely used in natural language model pretraining, which is often called n-gram masking or span masking. Such mechanism can prevent short-range dependencies, which improves pretraining quality. As shown in the slides, the corresponding visual tokens are also masked. We then replace the masked patches with a learnable embedding. The corrupted image patches are then fed into the multiple layer transformer. The final hidden states are regarded as encoded representations of the input patches. For each masked position, we use a softmax classifier to predict the corresponding visual tokens. The pretraining objective is to maximize the log likelihood of the correct visual tokens given the corrupted images. The masked image modeling task is greatly inspired by masked language modeling, which is one of the most successful pretraining objectives in natural language processing. However, directly using pixel-level autoencoding for vision pretraining pushes the model to focus on short-range dependencies and high-frequency details. Our work overcomes the above issue by predicting discrete visual tokens, which summarizes the details to high-level abstractions. Ablation studies show that our proposed method significantly outperforms pixel-level autoencoding. The BEiT pretraining can be viewed as variational autoencoding training. Let's consider the evidence lower bound of recovering the original image from its corrupted version. The first term denotes the image tokenizer that obtains visual tokens and decodes the original image given input visual tokens. In the first pretraining stage, we obtain the image tokenizer as a discrete variational autoencoder. Specifically, the first stage minimizes the reconstruction loss with a uniform prior. And in the second stage, we simplify the Q function to a one-point distribution with the most likely visual tokens. Then the second term recovers the visual tokens based on the masked image, which is our masked image modeling pretraining task. It shows that our pretraining process is well supported by the variational autoencoding theory. And for our pretraining setup, we train the BEiT model for both BEiT base size and also for the large size. And we use a codebook size with more than 8K. And our pretraining data is from the ImageNet, but here we didn't use any human labels for the pretraining. After we pretrain the BEiT model, we can append a task layer upon the transformer and fine-tune the parameters on downstream tasks like BERT. We take image classification and semantic segmentation as examples in our presentation. It's straightforward to leverage the pretraining and then fine-tuning paradigm on other vision tasks with our pretrained model. For image classification tasks, we directly employ a simple linear classifier as a task layer. And for the semantic segmentation task, our encoder can also be in-trained and fine-tuned in a very similar way. The table reports top 1 accuracy on image classification. We compare our methods with vision transformers trained by randomly initialized training, supervised pretraining, and previous self-supervised learning methods. All the compared models are base size, except IGBT has more than 1 billion parameters. Pretraining is conducted on ImageNet for the comparison purpose, except BEiT GFT is pretrained on Google's in-house 300 million images. Compared with the models trained by random initialization, we can find that the pretrained BEiT significantly improves performance on both datasets. The results also indicate that BEiT can greatly reduce the requirement of annotation efforts. BEiT also improves the performance on ImageNet, which shows a very interesting property, which is quite effective under the rich resource setting. Moreover, we compare our method with previous state-of-the-art self-supervised method for transformer, such as Deno and Moco. Our proposed methods outperforms previous self-supervised models on ImageNet fine-tuning. We train the pretraining tasks of BEiT and Deno together in a multitask manner. Augmenting masked image modeling with Deno improves semantic segmentation and obtains comparable results on ImageNet classification. Moreover, we found that BEiT is more efficient in terms of pretraining speed, as Deno has 2 copies of transformer parameters for self-distillation and multi-crop augmentation. Because BEiT is more memory efficient, we can use a much larger batch size to fully utilize GPU cards in practice. We further scale up BEiT to the large size. The results also verify that the data-hungry issue of visual transformers, where When training from scratch, we can find that the BEiT the BEiT from scratch performance is worse compared large to the base. In comparison, the benefits of scaling up BEiT from base to large are greater than supervised pretraining. The results suggest that BEiT tends to help more for extremely larger models, especially when labeled data are insufficient to conduct supervised pretraining for such large models. We also compare the convergence curves of the training from scratch and pretraining then fine-tuning paradigms. We found that fine-tuning BEiT not only achieves better performance, but also converging much faster than training BEiT from scratch. Moreover, fine-tuning BEiT can reach reasonable numbers within very few epochs. Then we evaluate BEiT on semantic segmentation benchmark. By appending a task layer based on upper net, we can fine-tune the BEiT backbone on the end task. Our model achieves state-of-the-art performance even compared with previous strong methods. We conduct ablation studies to analyze the contributions of each component in BEiT. First, we ablate block-wise masking by randomly sample masked positions. We found that block-wise masking is beneficial on both tasks, especially on semantic segmentation. Second, we ablate the usage of visual tokens by predicting the row pixels of masked patches. The pretrained task becomes a pixel-level regression problem to recover masked patches. Our proposed masked image modeling task significantly outperforms naive pixel-level autoencoding. The results indicate that the prediction of visual tokens is a key ingredient of BEiT. Third, we try to ablate the usage of visual tokens and block-wise masking together. We find that block-wise masking is even more helpful for pixel-level autoencoding, which relieves the suffering of short-distance dependency. Fourth, we compare BEiT with different training steps. Pretraining the model much longer can further improve performance on downstream tasks. We show that the self-attention mechanism in BEiT can separate objects, even though our pretraining doesn't rely on any manual annotation at all. The probing images are taken from the MS COCO corpus to avoid appearing in the pretraining data. We plot the self-attention map for different reference points within an image. The visualization are produced by attention scores computed via query key product in the last layer. For each reference point, we use the corresponding patch as a query and show which patch it attends to. After pretraining, BEiT learns to distinguish semantic regions using self-attention heads, even without any task-specific supervision. The property partially indicates the reason why BEiT is able to help downstream tasks. Such knowledge acquired by BEiT potentially improves the generalization ability of fine-tuned models, especially on small-scale datasets. Our contributions are summarized as follows. First, we propose a masked image modeling task to pre-train vision transformers in a self-supervised manner. We also provide a theoretical explanation from the perspective of variational autoencoder. Second, we pre-train BEiT and conduct extensive fine-tuning experiments on downstream tasks, such as image classification and semantic segmentation. Third, we present that the self-attention mechanism of self-supervised BEiT learns to distinguish semantic regions and object boundaries, although without any human annotation. Our code and pre-trained models can be downloaded from this link. Thanks for your attention.